Everything is moving. I mean, you are, the planet you're on, the galaxy it's in, it's all constantly in motion. But how do physicists actually talk about all this movement with any kind of precision? Well, it turns out there's a very specific language for it. And once you learn its rules, you start to see the world in a whole new way. So let's learn to speak the language of motion.
So here's our game plan. We're going to start with a pretty surprising idea that all motion is relative. Then we'll untangle the key differences between distance and displacement, and of course, speed and velocity. After that, we'll get into acceleration, see how it looks on graphs, and then finally, we'll wrap it all up with the really neat case of moving in circles.
All right, first up, a huge idea. All motion is relative. Now, that might sound simple, but honestly, it's a total game changer. In physics, just saying something is moving is, well, it's pretty much meaningless. The only question that really matters is, moving relative to what?
Okay, let's try a quick thought experiment. Just look at the walls around you right now. Are they moving? Well, from your point of view, sitting right there, of course not. They're at rest. But what if we could instantly zap our perspective out to, say, the moon? All of a sudden, those stationary walls are actually whipping through space at over 1,000 miles an hour with the rest of the Earth. Your perspective, your frame of reference, is everything.
So what this all boils down to is one simple, key idea. Motion is just a change in position relative to a reference point. Think about it. If you're on a bus, the person sitting next to you isn't moving relative to you. But to someone standing on the sidewalk watching you go by, you're both flying past. It's the exact same event, just seen from two totally different reference points.
Okay, so if motion is a change in position, how do we actually measure that change? In our everyday language, we might just use one word for it. But in physics, we need two very distinct tools, distance and displacement. They sound pretty similar, I know, but trust me, they tell us completely different stories about a journey.
And here is the core difference. Distance is what we call a scalar. The best way to think about it is like your car's odometer. It just keeps adding up the total ground you've covered, no matter how many twists and turns you make. It's just a number. But displacement, that's a vector. It doesn't care about the path you took. It's just the shortest, straight-line path from your start point to your end point. It has a size and a direction. It's the as-the-crow-flies measurement.
So let's dive a little deeper into distance, which physicists often represent with the letter S. It's simply the actual length of the path you've traveled, and we measure it in meters. The most important thing to remember here is this. If you have moved at all, your distance can never be zero. It's always a positive number.
Now for displacement. Again, it's that straight line separation from your start to your end. Picture this. You run one full lap around a 400-meter track. What's your distance? Easy, it's 400 meters. But because you finish in the exact same spot where you started, your displacement, your change in position from beginning to end, is zero. A big, fat zero. Okay, great. With distance and displacement sorted, let's add time into the mix. This naturally leads us to our next really important pair, speed and velocity. And you can probably guess the pattern here. One's a scalar, and one's a vector, building directly on what we just covered.
Speed is pretty straightforward. It's just how fast you're covering distance. It's a scalar, so it has no direction. The formula is just distance divided by time, and its SI unit is meters per second. You know the speedometer in your car? That's measuring your speed. It tells you how fast you're going, but it has no idea where you're going.
Velocity, on the other hand, is a vector. It's speed with a direction. So instead of using distance, it uses displacement. Now the formula looks exactly the same, v equals s over t, but here that s stands for displacement. So telling an air traffic controller a plane is moving at 500 miles per hour, that's its speed. But telling them it's moving at 500 miles per hour due north, now that's its velocity, and that little bit of extra information is absolutely critical.
Now, let's be real. Objects almost never move at a constant velocity for very long. They speed up, they slow down, they turn corners. Anytime the velocity changes for any reason at all, we need a new word, and that word is acceleration.
Acceleration is simply the rate at which an object's velocity changes. And yep, you guessed it, it's a vector. The formula breaks it down for us. It's the change in velocity, that's the final velocity v, minus the initial velocity u, all divided by the time it took for that change to happen. And its unit, meters per second squared. I know it sounds a little weird, but it just means how many meters per second of velocity are you gaining or losing for every single second that passes.
And we can get even more specific. Hitting the gas pedal in your car, that's positive acceleration. Hitting the brakes, that's negative acceleration, which is sometimes called retardation or deceleration. An object in free fall, just pulled by gravity, experiences what we call uniform acceleration. Its velocity changes by the exact same amount every second. But driving in city traffic with all the stopping and starting, that's a perfect example of non-uniform acceleration.
So this is all great, but how do we actually use all this stuff? Well, physicists have a really powerful toolkit for seeing and predicting motion, and it's all about graphs and a few very important equations.
Let's start with a distance time graph. It's a really simple but incredibly powerful way to tell the whole story of a journey. All we do is plot the distance from a starting point on the vertical axis, and we plot time on the horizontal axis.
And the really cool part is that we can read the story of the motion just by looking at the shape of the line. A straight, upward-sloping line means the object is moving at a constant speed. A flat, horizontal line, that means the object is at rest. Time is passing, but its distance isn't changing. And a curving line means its speed is changing, it's accelerating. And here's the key takeaway. The steepness, or the slope of that line, tells you the object's speed. The steeper the line, the faster it's going.
Okay, now let's switch gears and look at a velocity time graph. This time, we're plotting velocity on that vertical axis. And this graph, well, it's even more revealing, especially when we start talking about acceleration.
This graph tells us so much. A flat horizontal line means constant velocity, which means zero acceleration. A straight line sloping up or down shows us uniform acceleration or deceleration. In this case, the slope of the line is the acceleration. And here's a really cool trick. The area under the line on this graph actually represents the total distance the object has traveled. How cool is that?
Now, when we're dealing with that nice, predictable, uniform acceleration, we get to use these three incredibly powerful equations. They perfectly connect all the concepts we've talked about: velocity, acceleration, time, and distance. If you know any three of those values, you can use one of these equations to find all the rest. I mean, this is the very heart of predictive physics.
For our final topic, let's look at a special case that ties everything together just beautifully: uniform circular motion. This is what we use to describe any object that's moving in a circle at a constant speed. And this sets up a fantastic little physics puzzle. Now, we just learned that acceleration is a change in velocity. So if an object is moving in a circle at a perfectly constant speed, how on earth can it possibly be accelerating?
And the answer is a huge, definite yes. And this is such a key insight. You have to remember, velocity is a vector. It has magnitude, which is its speed, but it also has a direction. So even if the speed isn't changing at all, the object's direction of motion is changing at every single instant as it moves along that curve.
And that right there is the punchline. Because its direction is constantly changing, its velocity is constantly changing, and any change in velocity is, by definition, acceleration. So an object moving in a circle at a constant speed is always accelerating. It's the perfect example of why this language of motion, understanding the difference between scalars and vectors, between speed and velocity, is so incredibly precise and so powerful.